Hello dear students, welcome to Fourier Analysis-Ii. In this video we are going to learn about Fourier analysis, one of the basic and important topic of network analysis. We have covered the basic portion of Fourier analysis. In this video we are going to start from calculations for Fourier series coefficients for even, odd and half wave symmetry. That is your calculation for Fourier series coefficients for even, for odd and half wave symmetry. Okay, let us start the solution. For odd symmetry, as we have studied that n is equal to 2 by t integral from minus t by 2 to 0 f of t cos n omega t dt plus 2 by t integral from 0 to plus t by 2 f of t cos n omega t with respect to dt. n is equal to 2 by t integral from plus t by 2 to 0 f of minus t cos of minus n omega t with respect to minus dt plus 2 by t from integral from 0 to t by 2 plus t by 2 f of t cos n omega t with respect to dt. As the function ft as the function which is represented by f of t, ft is odd, therefore what we know that f of minus t will be equal to minus of ft. This is known to us as ft is our odd function. Similarly, on the other hand, we know that also that cos of minus n omega t is equal to cos of n omega t. So an is equal to 2 by t integral from t by 2 to 0 f of t cos n omega t with respect to dt plus 2 by t integral from 0 to t by 2 f of t cos n omega t dt. That is equal to minus 2 by t integral from 0 to t by 2 of f of t cos n omega t with respect to dt plus 2 by t integral from 0 to t by 2 of f of t cos of n omega t with respect to dt is equal to 0. Why? Because see this portion and this portion are equal and opposite. Call it equation number 1. But we also know that two by t integral from minus t by 2 to 0 f of t sin n omega t dt plus integral 0 to t by 2 f of t sin n omega t dt is equal to 2 by t integral plus t by 2 0 minus f of minus t sin n omega t minus dt plus 2 by t integral 0 to 2 by t f of t sin n omega t with respect to dt is equal to 2 by t minus 2 by t integral from t by 2 to 0 f of t sin n omega t dt plus 2 by t integral from 0 to t by 2 f of t sin of n omega t dt. Okay, I hope this is clear up to this level. This is simple trigonometric and calculus calculation here. This implies this equal to 2 by t integral from 0 to t by 2. Okay, f of t sin n omega t dt plus 2 by t from 0 to t by 2. The range of integration being the same here, of f of t sin n omega t dt. This is similar. This whole one is similar to this one. So it is coming the twice of this. So it will be like 4 by t integral from 0 to t half t by 2 of the function ft sin n omega t. Call it equation number 2. So this is your odd symmetry. This is the complete calculations for Fourier series coefficients for odd symmetry. Okay. Now let us move towards even symmetry. For even symmetry, similarly from the previous calculation, we can have A0 or A naught is equal to 2 by t integral from 0 to t half t by 2 f of t with respect to dt. That is an is equal to 4 by t integral from 0 to t by 2, that is f of t cos of n omega t with respect to dt. And we know that for even symmetry Bn is equal to 0. For half wave symmetry, we know that A naught is equal to 0 and An is equal to 4 by t integral from 0 to t by 2 f of t cos n omega t with respect to dt n is equal to 4 by t integral from 0 to t half and f of t cos n omega t dt. And Bn is equal to 4 by t integral from 0 to t by 2, 0 to t by 2, f of t sin n omega t with respect to t. This is for your for n is odd. For n odd, and the value of an is equal to 0 and the value of bn is equal to 0 for n is even. This is a complete half-wave symmetry, so we have to keep in mind this thing and this thing. When your n is odd, this is the possibility, two possibilities for an and bn respectively, and for when n is even, this is your n is equal to 0 and bn is equal to 0. This is widely used while having calculations of numerical. Okay, let us have the properties of even and odd functions. This is very important. This is widely used and we should all know. This will be very much instrumental and helpful while having calculation numerical. Properties of even and odd functions. Point number A, that is sum of even functions is equal to even function. That is sum of even functions is always even function. Okay. Point number B, sum of odd functions. That is sum of odd functions is always odd function. Point number C, even function multiplied by even function. You will get even function. Next point, odd function multiplied by odd function. That is odd function multiplied by odd function. Let me give you even function. Next point, if a function is neither even nor odd, then it can be represented as the summation of even and odd functions. Kindly have a look on this. If we have ft which is neither odd nor even, it is not clear that ft can be declared as purely even or purely odd. So ft can be written as partly even function plus partly odd function. That is the summation of even functions and odd functions. This is the even portion of function ft and this is odd portion of function ft. So what we are going to do now, put minus t in ft, we will have f of minus t is equal to fe of minus t plus fo of minus t. This implies f of minus t is equal to fe t minus fo t. So we can write it as fe t is equal to half of ft plus f of minus t. That is, even functions can be written as half of this f of minus t and f of t. First is ft and second part is your f of minus t. Likewise, f of 0t or fo t can be written as half of ft minus half f of minus t. Now, the Fourier series coefficients can be calculated as the Fourier series coefficients. Fourier series coefficients can be calculated as for an is equal to 2 by p integral from minus t by 2 to t by 2 f even cos n omega t dt plus integral from minus t by 2 to plus t by 2 f odd of into cos n omega t dt, bracket closed. Likewise, Bn is equal to 2 by t integral from minus t by 2 to plus t by 2 f even sin n omega t dt plus integral minus t by 2 to t by 2 f odd sin n omega t dt, bracket closed. So this is the complete Fourier series coefficients for function ft, which was initially not clear whether it was even or whether it was odd. It was not clear to us whether it is purely even or purely odd. So it was partly written as summation of even and odd, and from their point it was known that Fourier series coefficient of such functions can be written as like this: an is equal to 2 by t integral from minus t by 2 to plus t by 2 of even functions cos n omega t dt plus integration from minus t by 2 to t by 2 of odd functions cos n omega t dt. Likewise, Bn can be calculated as 2 by t integral from minus t by 2 to plus t by 2 of even function sin n omega t dt plus integration from minus t by 2 to t by 2 plus t by 2 of odd function sin n omega t dt. So let us move towards the next topic, that is your line spectrum. That is your line spectrum. Line spectrum is the plot which shows the variation of amplitude and phase of function with respect to n. Line spectrum is the plot which shows the variation of amplitude, which shows the variation of amplitude and phase of the functions with respect to n. The first part is your amplitude spectrum. Amplitude spectrum. What we have for trigonometric Fourier series given by the previous equations we have studied here. The amplitude spectrum is the plot between Cn and n. The amplitude spectrum is the plot between Cn is the plot between Cn and n, whereas Cn is equal to root under an square plus bn square. Let Fourier series of any odd periodic function is given by Fourier series of any odd periodic function is given by f of t is equal to minus 100 upon pi sine of omega t minus 100 upon 3 pi sine of 3 omega t minus 100 upon 5 pi sine of 5 omega t, and so on. In this series, there are only odd harmonics with sine terms only. In this series, there are only odd harmonics with sine terms only. The average value A0 and an is equal to 0. This is also 0 and this is also 0. I'm repeating it once again. In this series, there are only odd harmonics with sine terms only, and the average value of A0 and an is equal to 0 here. And value of Cn is equal to, it is root under an square plus bn square. N being 0, so it is bn. The line spectrum will be like this. The line spectrum will be like this. Zero, 1, So this is your amplitude spectrum. Cn for n is equal to 1, it is 100 upon pi. Cn for n is equal to 3, it is 100 by 3 by pi. Likewise, at n is equal to 5, it is 100 by 5 pi, and at 7 position, it is 100 by 7 by pi. 100 by 7 by pi. 100 by 7 pi. This is our amplitude spectrum. Now for phase spectrum, for f of t is equal to a0 plus summation from n is equal to 1 to infinity of Cn cos of n omega t minus theta n, where theta n is equal to phase of nth harmonic, which is tan inverse Bn by An. The phase spectrum is the plot of theta n as function of n or omega n. It is drawn as like this. This is your theta n, and this is your pi by 2. So it will be like this. And so this is your n-axis, and this will be like this is your phase spectrum. It looks like this. Let us move towards RMS value of function by its Fourier series. This is important. This is RMS value of function by its Fourier series. By its Fourier series. The RMS value of complex wave, we have seen this. The RMS value of complex wave, we have studied this. And we have also seen that the Fourier series of any periodic functions ft is given as ft is equal to a0 plus a1 cos omega t, a1 cos omega t plus a2 cos 2 omega 2 omega t plus dot 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 an cos n omega t plus b1 sin omega t plus b2 sin 2 omega 2 t plus dot 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 bn sin n omega t. Therefore, the RMS value of ft is given as that the RMS value of ft is given as f RMS is equal to under root a node square plus a1 by under root 2 whole square plus a2 under root 2 whole square plus dot 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 plus b1 by under root 2 whole square plus b2 by under root 2 whole square. This is complete. This is completely under the root, square root. We also know that we also know that we also know that Cn is equal to root under an square plus bn square, and FRMS will be equal to root under 0 square a0 square plus 7 square plus c2 square by 2 plus c3 square by 2, so on. So this is your FRMS. So let us move towards solved examples. Solved examples. Example number 1. Example number 1. Given the sawtooth function, of voltage waveform or voltage function of voltage function, find its Fourier series. Find its Fourier series. So we can have like this. This is your sawtooth function. How to draw the sawtooth function? This is your sawtooth function. This is your time axis T, and this is the Vt, and this is some constant K1 given to you. This is your origin, this is T, this is 2T, this is 3T. Okay, the time period is t. The time period of the given periodic sawtooth wave is t. It is obviously seen from the diagram given, and the maximum value is your k1. Okay, let us find out the expression for function for t greater than equal to 0 and lesser than equal to time period t. We have to find the expression for this periodic sawtooth function for this entire region, that is your from this one. After the capital T, the time period t, the function, the waveform is repeating itself, so it is advisable to just find the expression up to the time period capital T. See this is your Vt, this is your Vt, this is your function V of t. V of t is equal to k1 by t. We have followed y is equal to mx plus c. Mx plus c. C is your intercept when it is not given, so it will be just like this. M is your slope. Slope is founded by tan theta, that is tan theta. This is your theta value. So the slope is perpendicular by the base one. Tan theta is given by perpendicular by the base one. By this equation, we have this V of t is equal to, this is your slope k1 by t, and this is your x, which is here. So the expression is your k1 by t of t. This is your k1 by t. This is your k1 from here to here, and this is your t. And if this is your theta, the perpendicular will be this and base will be this. Okay. The slope is given by tan theta is equal to k1 by t. So it is Vt is equal to k1 by t. So the average value, for the average value, let us move towards for the average value, for the average value, A0 is equal to 1 by t integral from 0 to t, that is v of t dt is equal to 1 by t integral from 0 to t, put the value, that is k1 by t dt, that is equal to k1 by t square by 2 ranges from 0 to t is equal to k1 by 2. Since the wave has odd symmetry, so the coefficients of cosine terms will be 0, that is an is equal to 0.